using new technology such as ultra-high precision grinding. So I explained this project to my friend, Dr. Fujiwara. And everything has begun. And recently, Dr. Fujiwara made this homepage because he made a new company to develop a new telescope. And this is the first page of this company, Nano-Optonics Energy. The shift toward a nation based on the scientific and technological creativity. And this is an interview to him. Could you explain the background to the founding of Nano-Optonics Energy? In March of 2005, I had a phone call from Dr. Kazunari Shibata, who had been my colleague at Kyoto University. That was the beginning. He asked me if I was able to provide some financial assistance for the development of a new astronomical telescope. So I asked him to come to see me. He is in Tokyo, and explain the project in detail. He came over soon and explained the concept to me. Firstly, this is important. I felt that he was passionate about the project. Then I asked him to come again and let me know as to how far the project was progressing and what the chances for success would be. And then next time I took my colleague, Dr. Tetsuya Nagata, Professor Nagata, and also Emeritus Professor Maihara, both with me, visited and gave me details. In short, it was to build a telescope with a segmented mirror based on the technology called grinding. Since I believe this would work technically and scientifically, and we could try something new, I visited Nagase Integrated Company. This is a small company which has a very good technology. And he felt he can use this technology also for business. If the business is failed, he can think, I simply donate it. But if business is successful, he said, we can make a much larger telescope, like a 30-meter telescope. So that is his way. And this is some photo with him, myself and Professor Maihara and Professor Nagata in Kazan Observatory. And so this project started. And I will now explain more details about the telescope project prepared by Professor Nagata. What is the Kyoto telescope project? We have a university consortium, including Okayama Astrophysical Observatory, National Astronomical Observatory, and Nagoya University, and also other small universities. And we use a new technology, especially that is important, educating graduate students. And this is a first step for making a future giant telescope, extremely large telescope, such as a 30-meter telescope. And as I explained, this is the first example of a telescope supported by private fund. As you know, in the United States, there are many astronomical telescopes have been developed by private company, Keck, I'm sorry, I forgot. Palomar telescopes also, and Mount Wilson also supported by private company. And so we will develop a new technology, such as ultra-high precision grinding, 18 segmented mirrors, and ultra-light mounting. This. By the way, this is an 8-meter Subaru telescope. This is one mirror. This would be the first segmented mirror telescope in Japan. And this is the site in Okayama Observatory. Now we have a 1.88 meter telescope here. This is the site for a 3.8 meter telescope. This is a hill of the small mountain. And we have 6 mirrors here and 12 mirrors around with this size. And focal length is 5 meter, rich gradient. Using ultra precision grinding. Here previously, of course, everyone knows, mirror has been made by polishing. This is very smooth, but needs long time. Usually need 1 year to make a 1 meter mirror or so. But we use grinding. This is a wet stone rotating very rapidly and cutting. Amazing. And as I told you, a small company, Nagase, at Gifu, had already developed this kind of a technology. And they, of course, they are making a very nice mirror and so on, lens and so on. But interestingly, they don't know how precise their technology. So astronomer can help to measure the accuracy of the mirror by using the interferometry. And this is a grinder completed in 2007, December. The price of this grinder is nearly $4 million. And that company, small company, the business is to sell this kind of a grinder to other bigger company like Nikon or Canon and so on. And here is a wet stone located. The resolution is 1 nanometer, pointing 10 nanometer. And infrared astronomer of Nagoya University helped measuring the accuracy of a mirror by using the CGH interferometer developed at Nagoya University. Professor Shuji Sato's group. And this is a detailed storage. Sorry in Japanese. But anyway, here light is emitted, and anyway, eventually, it's not easy to explain this, but maybe some of you already well known. These are very useful to measure the accuracy of the mirror plane. And recently I visited first experiment. This is myself, and looking at this kind of experiment. You can understand how laser and reflected, and both making interferometric pattern and so on. This is the example of grinding, measuring the smoothness of a mirror. And this is the 100 nanometer. Still, of course, we need, finally, we need polishing to make a best mirror. But at first, grinding is very fast. That is very useful. And if we overlay all same, so reproducibility is very good. Okay. And this was measured with the laser displacement meter. Oh. So please help me. Okay, thank you. So this is a test picture of a test grinding. This mirror material itself should be developed, and we are using 610 millimeter clear ceram Z, which was introduced by Ohara company, zero thermal expansion glass. And as I showed you, this is a picture of when grinding. So I'm very much impressed by recent high technology, amazing. And also Dr. Fujiwara was very much impressed by this high technology. This is again the example of measuring the smoothness, and by the end of this December, probably first mirror will be created. Still going on. This is also a picture when grinding. Anyway, this is a first development of this kind of technology for astronomical mirror. This is another technology. In Kyoto University, students are developing this kind of trusses to support this mirror and controlling. One mirror with a roughly 1 meter size is supported by 3-point support. And the distance is measured by this kind of instruments, phase matching. And this is evidence that how matching is good. This is the third technology to make ultra light mounting, developed in Nagoya University groups. Here, very simple. Maybe your new 10-meter telescope may have a similar one. This is an example. Truss structure. And this is very recent one. One part structure is being constructed. Elevation axis. Okay, so using these new technologies, we are now going to develop a new telescope. And this briefly explains astronomical science target. One is a high time resolution for relativistic objects, such as gamma ray bursts, black hole binaries, and supernovae, and so on. Also, personally, I'm very interested in the stellar flares, which may affect the planet around the stars. It's important for astrobiology. And we hope to observe the second time scale fluctuations. This may be produced by synchrotron radiation by high energy electrons, and short time scale fluctuation in gamma ray bursts are already well known. We want to observe such a very high time variability. This is the example of Cygnus 1 short flares. And why we put our telescope in Japan? The reason is that this one. This figure shows 3 telescope sites with more than 3 meter telescopes larger than 3 meter diameter. So the region around Japan is nothing. So if gamma ray burst occurs at the night sky of Japan, no data is taken in the world. So we have to put at least 3 meter class telescope around Japan, East Asia, for the worldwide astronomical research. So this is one important reason. And also, of course, 3 meter telescope in Japan is very useful for education. And this is another scientific target, that is infrared high-resolution spectroscopy, detection of weak absorption or emission lines, like hydrogen quadrupole transition. This is a subject of Professor Nagata. He's an expert of observation of the star-forming region. So I'm not so familiar with this. But anyway, this kind of spectroscopy, high-resolution spectroscopy, is also useful for detecting extrasolar planets. I'm interested in more about extrasolar planets. So some years ago, we had a press release like this. And anyway, this is the first historical event that private company donate such a big telescope to university researchers. And also, this is a collaboration between Kyoto University, Nagoya University, and the National Astronomical Observatory, and a private company. And we want to extend such inter-university collaboration more. This is the Kyoto University, National Astronomical Observatory, many universities, small universities in Japan. And also, for outreach, this is very important. This is one example. Hiroshima University recently installed 1.5 meter telescope. So using those small telescopes to observe a transient object would be very effective. And with 3.8 meter telescope, we can observe the spectroscopic data. So that is very important. So our Kyoto University group can be a domestic center for optical and infrared researchers all over Japan, sharing home telescopes, collaboration and education support, and under steering committee. And also, as I told you, our project is based on the private fund by Nano-Optonics Energy, Inc. But we also want to get governmental fund, which is not yet successful. But my friend already told me, oh, you don't need the Japanese government. I can help you everything. But anyway, we are always trying. From this sense, international collaboration, if possible, that would be very useful. We need a operation budget $0.5 million per year. In future, it will be easy to make exactly the same telescope with cheaper budget if first telescope is completed. And I myself personally hope to put the 3.8 meter telescope in many other countries with different longitude to do a continuous observation of a transient objects. And also, I want to extend our study to search for extrasolar planets and life in the universe, astrobiology. By the way, I'm also involved in the solar research. And in the solar research, we are now doing a chain project, continuous H-alpha imaging network project, by putting a small solar telescope in many other countries in different longitudes to do a continuous observation of solar activity. And I think we can do exactly a similar one. This is a solar continuous H-alpha imaging network, Hida, Peru, and recently we are discussing Libya, Algeria. But we can mimic similar project with 3.8 meter telescope, whole Earth 3.8 meter telescope network, starting from Japan. And Professor Nagata has already collaboration with South Africa. And here, I hope to have such an international collaboration here. And we have also good relation to Peru or Chile. So if this is possible, we can continuously observe transient object extrasolar planets with this high spatial resolution, spectral resolution telescope. So this is a future schedule. First slide, we hope 2012. And as I told you, first mirror will be completed this year, hoping. And this has been already finished. And now testing this one, segmented mirror technology. But we have not yet discussed the instrumentation yet. That is our problem. So summarizing my talk, Kyoto 3.8 meter telescope project is first university consortium project, including National Astronomical Observatory, and a new technology telescope. This is also very useful for educating graduate students. And also a first step for future giant telescopes by our technology. And the first example of a private fund telescope. And the new technologies are mirror manufacturing by ultra-high precision grinding and controlling 18-segment mirrors and ultra-light mounting. Coming soon in 3 or 4 years, and this is a future dream. Okay, that's all. Thank you.
Thank you very much for this very interesting talk. Now it's open for questions.
I have a question about the primary. If I well understood, the segments, the shape of segments are already defined and so on. Apparently they're different from the typical hexagonal segments. What do you expect in terms of PSF quality at the end, about controlling this PSF, and what can be the impact also on the image quality, since you don't have real symmetric, or I don't know, it's quite different shape. And actually the second question is just aside is, what are the typical observing conditions in Japan?
Okay.
Yes, you have big cities. I mean, for instance, the typical seeing you have in this radio vapor, this kind of things. Thanks.
I have a similar question to my colleagues always. And fortunately or unfortunately, the sky condition in Japan is not so good compared with here. So, where is the astronomical site? This is This is Okayama Observatory. This is close to a bit medium city, Okayama. This has 500,000 people. This is industrial region. So very bright at night in optical wavelength. Scale? Yeah. This distance about 30 kilometers or so. And this is, yeah, as I told you, this is not a high mountain, only a 300 meter mountain. And and the seeing condition is also not so good. This is in Japan. But in infrared, I heard, in infrared, seeing condition and light condition is as good as Hawaii. And the infrared is a longer wavelength, so easier than optical, controlling such accuracy of a segmented mirror. So if we apply this telescope to a best site in the world, like here, probably we need more high accurate technology. Yeah. Yeah. Yes, of course. Yes. And yeah, during lunchtime, I already discussed with Professor Rebolo. In Japan, the number of researchers, technicians, not many. So even with the fund to develop instrumentation is not easy. So therefore, if we can have international collaboration about development of instrument, that would be very helpful for us. And it's a very good excuse to convince the government to prepare money. So if you have a good suggestion for instrumentation, yeah, I'm very happy to hear. Yeah. At present. Yes, of course. I'm sorry, I don't have most recent data, but I think already a factor being better. And as I told you, finally, better to use a polishing. But to use both grinding and polishing is also new. And the people are now fighting with such a new experience. And eventually, of course, as I told you, yeah, I'm sorry, I don't remember exact number. But this technology has been already applied to one part of a small telescope mirror. And this is a larger 1 meter size. So we need more experience. But sorry, I don't remember what recent number. Yeah. Mm-hmm. 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 Yeah, yes. Mm. Yeah, that is a good question. Yeah. As a director of observatory, I think telescope with a diameter larger than 2 meters is necessary. And 3 meters is enough large. But astronomers, observation astronomers, want even larger telescopes. Yeah, so that is the reason. Probably to observe galaxy, this size is necessary. Yeah. Did I tell you the cost of a first telescope? Okay, it's not easy to say in English. I asked my friend to prepare $10 million. $10 million first telescope, but this seems not enough. We need to make a dome operation. And several months ago, I asked my friend to prepare $2 million to convince my university colleagues that this is a real project. He agreed, but at that day, Dean of Faculty of Science asked me to prepare money for making dome. So immediately I asked my friend to add more. So this is a current budget for first telescope, but not including instrumentation. But I think second telescope, at least this may be a smaller number. So this order, in total, yeah, how do you think? I'm not expert on instrumentation. This may be enough for a second telescope. I'm not so sure. Maybe you know better. By the way, this includes all operation instrumentation for a second telescope. So,
you show a sheet that costs $4 million. Is that included here, or is it separate money that you have possible to
doesn't include.
It's not included.
So, yeah.
That has been made.
Okay. Please remember, this value is what I would ask government to prepare. Of course, this is, will not be approved. But even 70% may be enough. So usually when we ask government, we will tell the maximum value. Mm-hmm.
So what is the relation between these two, the one that are both and the two, and the two different things that are created by?
That is a good question. Yeah, actually the number of optical infrared astronomers are very few. And Professor Maihara, he is an emeritus professor now. He is a key person to develop EFMOS. So simultaneously, he is developing this telescope as well as the EFMOS for Subaru. So, yeah, not so easy.
Any other question?
It was not clear to me if it is optical optimized and infrared as well, or just infrared. And in the case that you have optimized it only for infrared, would it be much cheaper?
Are you asking the only infrared?
This design is optical and infrared.
We hope both optical and infrared.
So in the case that you wanted only infrared, would it be much cheaper?
That's also a good question. I don't know so much, but they never says, the expert, my Professor Nagata and Professor Maihara, have never said so. So I think not much different, I think. Maybe some of you may know more. How do you think?
It seems that you are already pretty close for the quality you need for observations at 2 microns. Okay. Mm-hmm. Now the polishing will add extra cost. That will be safe if you just go for infrared observations. But I think we'll do more compare with investment. It seems. If you want to do observations at 400 nanometers, that's perhaps.
Well, by the way, we hope the time to make 1 mirror less than 1 month, and the best time 2 weeks or so. 1 meter mirror. 1 meter mirror.
How many segments do you have?
18.
Any last?
I don't know if you have mentioned, but what is the focal ratio of the telescope?
Focal ratio. Not here. Let's check. Focal length per meter. Okay. Don't ask me so much about instrumentation. Okay, enough. Okay, thank you.